Good afternoon, everybody. You're welcome to today's seminar series, April seminar series of the Numerical Analysis Research Cluster. And today's seminar seminar talk will be given by Dr. Dasumani Munkaila from the Pan-African University Institute for Basic Sciences, Technology and Innovation, PAUSTI, hosted by the Jomo Kenyatta University in Kenya. And Dr. Munkaila will be giving us a talk titled Discrete-time Optimal Control of Species Augmentation for Predictor Prey Models. In this talk, he will present a discrete-time optimal control theory that applies to two models of species augmentation for predictor-prey relationships. And two models representing different order of events of optimum augmentation timing are considered. And the reserve and target population are subjected to some strong Allen effects, and is going to solve numerically using discrete version of the forward-backward sweep method and the sequential quadratic programming iterative method, respectively. I will call on Ms. Fester to read his biography so that let us know who Dr. Munkaila is. Ms. Fester, over to you.
All right, good afternoon, everyone. Can you hear me?
Yes, we can hear you.
All right, so I'll go with the bio sketch now. Dr. Dasumani Munkaila is a Ghanaian mathematician who earned his master's degree in applied mathematics from Kwame Nkrumah University of Science and Technology and holds a bachelor's degree from the University of Cape Coast. He recently completed his PhD in applied mathematics at the Pan-African University Institute for Basic Sciences, Technology and Innovation, hosted at Jomo Kenyatta University of Agriculture and Technology in Nairobi, Kenya. Having successfully fulfilled his doctoral requirements and received his official PhD award letter, he is currently awaiting graduation. Mukaila's research expertise lies at the intersection of mathematical biology, ecology, and optimal control theory. His work utilizes numerical modeling techniques, including ordinary differential equations, discrete difference equations, and fractional calculus to address complex biological challenges. Thank you.
Dr. Julius, I think you are muted. It seems you are talking, but you are muted.
Sorry, Dr. Munkaila, please. Thank you so much. Yes, I was muted. Please, you are welcome to share your screen. Thank you very much. And start your presentation. Excellent. Good to see your face again, Dr. Munkaila. We cannot hear you.
Sorry, I think I was muted. I say thank you very
Okay.
much. We are hoping to come and meet at your place one day. It's a long time we met.
Yes, yes.
Yes.
Please share your screen.
Okay, yeah, I'm sharing. Kindly confirm for me if it is visible. It's okay. Dr. Julius, confirm for me or
Yes.
anybody the screen. Okay.
Yeah,
Okay.
fine.
Because of the network issue, I wish to mute my video and then yes. Okay. Thank you, Festa and Dr. Julius, for the introduction. And then we thank you very much, Dr. Julius. You have been working hard for this NACA mathematics curriculum to keep on going. Yes, thank you very much. And then it gives us opportunity to also showcase work we have done. As my name has already mentioned, I am Munkaila Dasumani. This work is a joint work. That's parts of my PhD work. It was supervised by Professor Susan Lennart and then Dr. Gladys and then Dr. Stephen Moore. So it's a joint work between these my supervisors and myself. And I'm presenting discrete time optimal control of species augmentation for predator-prey model. Why this topic is very important because as a human being, we need a balance in the ecosystem. We need to also study the ecosystem. We need the species. The animals are there. They are very important to us. We cannot be, there's no life for humans without them. We just coexist together with the animals, so we need to study them. The presentation outline are just very few here, and then I'll give very few motivations about the talk, and then I proceed. So these are some, we have two pictures, A and B, or figures. Figure A shows a leopard catching a prey. This one was captured in the Zambia Lungwa forest. And also we have I think, sorry, I need to minimize this. Okay, the right hand side, you have leopard and hyena feed on the same limited resource. That is a zebra. That is also the competition relationship. And these animals are in the forest and then they are competing and then they have to. I don't know. Did I lost?
Yes, we lost you. We lost you.
Oh,
Yes.
I'm sorry. I'm sorry. I'm sorry.
No
So
problem.
it means that, but my screen's already. It means I have to start again. Oh.
Yeah. Sorry.
Sorry. I was presenting because I saw it was reconnecting. Then I saw I was lost. The
Sorry.
internet has not been stable today here because we have blackout.
Wow.
Sorry. Okay. So Dr. Julius, do I have to start over?
Well,
I don't know where I lost. Okay, I was just on the second page.
Yes,
Okay, I was just here about. I
you
was
are
talking about the two
exactly.
figures. I hope I was there.
Yes, that's where you
All
are.
right. Oh, sorry. I said that these two figures shows a leopard catches prey in the Lungwa forest, and then we have the bee
sorry, Dr.
leopard.
Mukaila. Sorry, you might have to put full screen preview, please. Full screen.
Oh, okay. Into presentation mode. It's okay.
Thank you.
All
Thank
right,
you.
thank you. So the A and B figures indicate that these animals are into competition and then predator relationship in our forest, and it's going on. It's affecting the most of the animal population, and you can see those in the red, the Zanzibar leopard, and then the in Brazil, in Tanzania, and then in China. All these animals they have gone extinct. The last surviving species is dead. We don't have them again. They have gone because measures were not taken into places. And then these are also another animals that have gone on extinct. You can see the dodo bird. I was talking about the dodo bird because the dodo bird it's used to be a very important animal because its meat was meant for the chiefs and then for the people with high ranking in the society. But however, because measures were not put in place to conserve them or preserve them. The last surviving dodo bird is dead, and we cannot get them again. And not only that one, we have so many of them. So we have the extinct animals. They've all gone on extinct. We don't have them again. They've all gone. So the question is, how do we safeguard existing species? The that are on the verge of extinction. It's continual in this society. What is going to happen? So we start with the background of the study. Thousands of species are now being seen as vulnerable. Them are on the verge of extinction, though there have been so many efforts by the United Nations, UN, and so many stakeholders. However, predation, competition, and over contribute here to a lot of this species extinction. Species augmentation, I highlighted the predation because I'm going to talk more about the predation. My work was on predation. Is one of the methods used to promote biodiversity and prevent target or endangered species loss and extinction. And some augmentation studies have been conducted, and then the results have been successful. This is a very few of them. Some of them is the optimal translocation strategy for saving the black rhino in South Africa. In South Africa, the black rhino was going on extinct, so they tried the translocation process. They moved the animals from one place to come and augment the declined population, and now they have a lot of rhinos in South Africa. And then this one, 1990, in Montana Mountain in Florida, US, they brought 8 panthers to come and release them there. In 2023, it has been shown that they have over between 120 and 230 adult panthers in the population. It means that when the panther population was not there, they translocated some to go and augment, and now they have a lot of panther populations there. It means that this augmentation strategy has also been successful. So now I'll just talk about brief about the discrete-time predator-prey model, because the work is more about discrete-time predator-prey models. And then we also look at the order of events and then possibly some simulations. Many species with non-overlapping duration in their populations, what we mean here is that when they have birth rate and death rate are evenly distributed, it's not specific. So when the birth rate are evenly distributed, so they generally occur over a few months or maybe a week, years. It's when these populations are there and you want to model because they have a special life cycle, like elephant. They don't give birth at any time. They have a special life cycle. Unlike human being, every day somebody is giving birth, somebody is dying. So that becomes overlapping generation population. We can use ODU to model because it's continuous. However, if the population's life cycle is not continuous, we cannot use ODE. It's not the best strategy, best tool to use to study. Therefore, it's calls for us to use another approach, that is a discrete case, whereby we can now study the distant times where these species are okay or are interacted. So the interaction between predators and prey in ecological system can also have a very negative repercussions because when, according to the competitive species principle, when two species compete for the same limited resources, one will go on extinct. And when we have two predators competing for one prey, definitely the prey will go on extinct. And the predators, so at the end of the day, they're also going to have competition among them. And then we have this a global population size of the Hairola antelope. Hairola means that peace. It is a Somali language. Somali, this one is part of the northeastern Kenya. They have this antelope, Hairola antelope there. It is now considered as the most endangered antelope or threatened antelope. And the result is that because of predation and then habitat loss, they are now very endangered. And so many studies have been conducted about these populations. So predation can cause loss of extinctions. And then, so these lions, cheetahs, and African wild dogs are their primary predators. And then the problem here is that they have tried so many ways to safeguard these species, but it has failed. And now they have been considered as to be the most endangered antelope population in the world. And they are very important because those species, you can see their picture at the background, they symbolize peace. So we need a critical augmentation strategy to safeguard them. And then we also have other possible or other target species because of predator-prey relationship that are on a critical verge or critical stage on going extinction. You can mention some of them The woodland example is the Rangifer tariduska. That is a botanical name or scientific name. That is in the Colombia, and then also Australia. We talk about the fauna. They will have so many of them. Example is the Eastern Batten, and then Africa here we have so many of them, as I've indicated one in Kenya. And every country we have them. Even Ghana here we have them. The elephant population we have a very challenge in them because they are going on extinct. At first, when you go to the forest, you see the animals, but now they are all going extinct. How do we safeguard them? So in this work, we consider three populations. You consider the U as their prey population, and then we have V as our predator population. And then we have another population as W, which is our reserve population. And these are the vector that denote the respective populations. And then we have the time step, which is the subscripts. That is the time step for each population. Because we are doing discrete case, we represent the population densities by these time vectors. So with that augmentation effort, there's no augmentation. We assume that when we don't have augmentation in the system, then our equation 1 becomes our model for the interaction between the three populations, whereby we have the U as a prey, V as we have U as a prey, V as a predator populations, and the W is our target or the reserve population. But here, the target population is now our U population, the prey population, because due to the predator interaction on the prey, they are going on extinction. So therefore, our target population here is the U population. And then we have the S, and then that will be the growth rate. And then we have the delta 1, which is the consumption rate of the prey by the predator. We have the delta 2 is attack rate because it increases the predator population. And then we have the natural decay rate, the gamma. That one is natural decay of predators. Whether we have prey or we don't have prey population, the predator population may die, they can die. So that's the natural occurrence rate. And then we have the Q is the growth rate for the reserve. So here the reserve populations are kept in a separate environment whereby they are going very well with a lot of protection and a lot of food such that we can have enough individuals to harvest them to augment the declining population. And here we are considering Allee effect. We have two types of Allee effect. We can have weak Allee effect and strong Allee effect. But this model, we are considering the strong Allee effect. So the strong Allee effect is denoted by the M and N. So with the strong Allee effect, we have a critical threshold such that below that threshold, the population will be growing negatively or growing towards extinction. And above that rate, the population will be growing very well. So another assumption is that the prey population here, that the U population, we assume that they are below the strong early threshold. So they are on the verge of an extinction. We need to augment them. But the predator population is growing very well, so it doesn't have a threshold. And then the reserve populations have a threshold, that is M. N. That's also here. We are assuming that is growing very well because they are under protection. So that is the model when we don't have any optimal control, or when we don't have augmentation effort. So here, if we let the FU of V of T and then FV of V and then FW to be the functions of either the decay, the decay one is when the prey is decaying. So we have the decay function, the growth function here, we have the decay function here, and then we have the growth of the reserve population here. Then we can have the model as an order of event here. So this is the model equation 3, so that it becomes very simplified version. So you can see that the red one here, which is the growth function, is the growth of the prey population. And then so here the order, what happens here is that because we don't have any control here, the prey population will grow. When they grow, the predator-prey interaction will happen. At the end of the day, the predator will decrease because after feeding on all the prey population, there wouldn't be food for them again. So what will happen? They will start decaying. So that's what will happen. And here the reserve population is decoupled. You can see that it's decoupled because it doesn't depend on any other population. So here we don't factor this into the order of event here. Now the goal here was to develop an optimal control strategy for the model. So therefore, two discrete time augmentation models representing different orders of events are developed. So we have two models. The main two orders of events are here. The first one is model A. The model A here, what we assume is that growth of the prey population, so growth followed by predator-prey interaction and then augmentation. So the prey population will grow, predator-prey interaction will happen, and then we do augmentation. And the next one is that we do augmentation at the early stage. And then when we do augmentation, then followed by the growth, and then predator-prey interaction also happens at the same time. And then augmentation controls, because you are doing augmentation controls, are choosing to maximize the prey, the target population, because that is our interest. And then the reserve population, we need to also maximize the reserve population. We don't want them to go unextent. We need to also maximize them at the final time. At the end of the day, we also need to minimize the cost. Since we are going to translocate them, we need fuel, we need a car, we need a human labor, we must be paying. So there's a need to also consider the cost whilst we are maximizing the population, you need to also minimize the cost involved. And then the time step, I'll talk about that in the equation because we can see that the time step is less minus 1. I'll talk about that. So here becomes the model A, whereby I mentioned that the model A here, growth come first, followed by predator-prey interaction and then augmentation. So that's what happened. So we have our growth will come. The black one are all without the control. The black one is one. Augment the prey population. It means that the prey population and then the reserve population are of the same species. I don't know. Can you hear me? It's like my internet is not being stable. It's okay.
We can hear you, please. We can
All
hear you.
right, thank you. So here we are moving from the reserve population to augment the declining population, which is the prey population. That is the augmentation function AW of T. And then, as I mentioned that I'm talking about the T here, so you can see that the control, unlike the state variables, the state variables have additional variable than the control. And the reason is simple. The control are the driving forces. They are the input. You give me the input, I give you the output. Give me the input today, I give you the output tomorrow. So it means that you input the control, the state will give you the output. That is why the state variables have additional variables than the control variables. So now by substituting the required functions into model 4, we get model 5, which seems very complex, but model 4 explain it very easy. And then, so that is the model A. Now we want to look at model B. Model B. So for model B2, what happened is that the reserve population is first harvested. We firstly harvested the reserve population, and then to augment the target species, that's the first thing to do. And how do we do that? All to do is that you just need to substitute the function, the ut plus htw, and then that becomes where they are growing, and where they are harvesting is where we have the minus into the respective growth function, and that gives us model 6. So in the model 6, you can see that we are harvesting from the reserve. The blue one is now the added one, and where we have the augmentation. The black one is when we don't have augmentation. So we harvest from the W to now augment the U population. But when we are augmenting the U population, let's bear in mind that the predator population is also feeding on they are also feeding on the prey population. So automatically, when you augment the prey population, you provide enough food for the predator population. That is why inside the predator population, there's some form of the harvesting or the augmentation component, because it automatically increases the predator population. And then when we substitute the respective functions, we had the compressed interaction, which is 7, the equation 7. That is augmentation followed by predator-prey interaction, augmentation followed by growth, and then predator-prey interaction. You augment first, and then the growth and then predator-prey interaction also happen. That is model B. So now the objective is to maximize 8. So the 8 is such that's the objective functional. We are maximizing the total populations and then we are minimizing the cost. So that's the minimization strategy of the cost. And then we are maximizing the population. And then here we are also considering two cost functions or two cost scenarios because we have a linear cost and we have quadratic costs. Everything in society is non-linear. Sometimes some things can be linear. So here we are considering both linear and quadratic cost. And then these are our administrable control set. That is 9. It's the control set. And then we have h of t. H of t is very important. That is the control effort. And it's between 0 and A. And A is the maximum effort because we cannot move all the individuals to go on augment. They are also important. So it's a portion we are moving. So where A is the maximum effort we are taking in place. And we have the weights for balancing the cost. And then we also have as I said, that it's both linear and a linear combination. That is the cost is both linear and a linear combination. Okay, so now we are applying the generalization. The Pantraean maximum principle is for ordinary differential equation, ODE, but a similar method can be adopted for discrete case. So when we apply the generalization of the Pantraean maximum principle for the optimal control for the discrete system, and then we form the Hamiltonian function as 9, and then now we test for the Hamiltonian function if it satisfies the concavity condition before we can use the forward-backward sweep method. So after testing equation 11, we realize that second derivative test give us negative. When we have negative, where M1 is automatically positive, therefore it's satisfied. Once it's satisfied, we are free to use the discrete version of the Pantraean maximum principle to solve for the optimality system in 11. So that is model 1. And then this is also for model B, model A. So the first one is for model A. Now the second one is for model B. For model B2, we also form the Hamiltonian function. And then now we want to see if the Hamiltonian function will satisfy the concavity condition. But the model B Hamiltonian function can be written in the simplified version as 13, whereby R1 up to R4 are the various coefficients. So by finding the second derivative test, we had 14. You can see that we have 6R1 minus 2. So we cannot tell whether this is negative or positive. And the reason it means that the h of t is difficult to calculate to show whether it is negative or not. So finding optimality condition here is very difficult. And the reason is that because of the complicated dependencies on the control. When you look at the equation 14, you see how it was controls were inside. It was very complicated. Therefore, we cannot use the forward-backward sweep method to solve for the optimality system in model B. So we can use direct iterative methods. So we have so many of them. So by here, we chose to use the sequential quadratic programming. Sequential quadratic programming, iterative method. It's iterative method. So these are now we are solving the model A using the forward-backward sweep method. And because of the concavity condition, we cannot solve the model B with that method. We are solving model B with the sequential quadratic iterative method. But this is there's a summary of the forward-backward sweep method for model A. First, initial guess is made for the vector of optimal controls, and then the second step is to solve for the state vectors forward in time. The name suggests forward, backwards. The state variables are having initial conditions, so it's easy to solve them using the initial conditions. And then the next step is that because the states, the adjoint equation, they don't have initial conditions. However, they have some boundary conditions. Therefore, we can solve them backwards in time. So we solve for the adjoint equations backwards in time. And then here, the control is updated from the characterization of the optimal controls with the adjoint and the state variables. And then the control, finally, the updated control is used. So this is used over and over until the tolerance or the difference between the successive iterative is very close. So when the tolerance is reached, now the system will output the best optimal control strategy. So that's the forward backward super method, summarized form. And then the sequential quadratic iterative program method for model B. Similarly, the same thing, initial guess is made for the vectors and then vector optimal controls, and then one using the initial conditions. But what's making here different is that the initial gradient of the objective functional is computed, which will be used in the construction of the quadratic subproblem. The problem is that the idea is that it will convert the problem into the quadratic subproblem, which is easier to solve. That is sequential quadratic iterative method. So the next step is the formulation of the quadratic subproblem, and this one is obtained by the approximation of the Jacobian, that is the objective functional, and then the linearization of the state constraint. And then we also employ this function in the MATLAB fmencon solver, which also carries the SQL sequential quadratic programming algorithm. And then we were able to solve the quadratic subproblems. And then here the control is also updated and the state variables, and then all the state variables are also updated using the newly updated control. After that, the new gradient of the state variables and objective functionals are computed to check for convergency because it's very important. Now here, the algorithms, if the Kantaka condition for optimization holds, then it will stop. If not, it will increase the time step by 1. Then it will repeat the process until the KKT condition is achieved. And then the KKT condition in optimization is achieved when there's to be 0.25, which is 25% of the carrying capacity of each population. Let's bear in mind that the M is the strong Allee effect for population U, which is the pre-population, and the N is for the reserve population. Dr. Juros, can you hear me?
We can hear you. We can hear you. We can hear you.
Oh, okay.
Please put the presentation mode again.
Yes.
Thank you. Thank
It's
you.
okay. All right. So having that said, now we assume the population units are also 1,000 individuals with the initial conditions, 0.20, 0.5, and then 0.70. Here, we can see that it also agrees with the early threshold, which is 0.25. The pre-population 0.20, which means that it's below the early threshold. It's growing extension. And the predator population 0.5 is growing well. Look at the reserve population 0.70. It is highly above the early threshold. This means that we have enough individual to harvest for augmentation. And then we use the baseline parameter values. That's our equation 15. You can also find them in the reference 2. And then at the end, we also compute objective functional values. I'll talk about that. They are very important. So these are the baseline plots for model A using the forward backward method, and then also using the baseline parameter in 15. So we have pre-population, reserve population, predator population, and then control. Now we can see that we have the dots black line. The dot line indicate the early threshold. So when we use those parameters, the red plots in the pre-population and predator populations are the plots without augmentation. So when we don't have augmentation, we can see that pre-population is declining. It's going on extension. It's just declining. So by 6 years, it is always, even from 0.2, it's almost getting to 0.05 or even below 0.05. It means that it's going on extension. But as soon as augmentation set in, the population started increasing. By 4 years, now it's increasing up to 0.3, which after here, even if you don't augment them again, they can grow on their own because they have enough individuals. And the same thing happened to the reserve population. You don't want them to go in extension. So you can see that the reserve population, the red one, is growing very well, 0.8, very high. Initially, it was 0.7. But when we started augmentation, their population level reduces. The blue one, it reduces, but it's still 0. Let's say 0.55, 0.55, which is also higher than the threshold for growth. So here, the augmentation has been successful. Because look at the predator population. The dot line was when we don't have augmentation. But when augmentation came in, the predator population has increased a bit. Though we were not augmenting the predator population. After augmenting the prey population, there have been a lot of food for predator population to also eat, and their population also rises. So this shows that augmentation has been very successful. And we have the objective function. And when we don't have the optimal control, the cost is 0.4413, but when we have the optimal control where we have the star, the cost increases, but it indicates only 11% higher than when we don't have control. That means that we have less cost incurred, but we have a lot of augmentation taking place. That is for model A, whereby we do augmentation, and then predator prey will come, and then we have model B here, whereby also after also doing the plot, the same thing, but the difference between the two models is that look at the model B here. You can see that the prey population, even after augmentation 6 years, the black one after augmentation, still the level is below the threshold for growth, and then without augmentation, it's still declining. And then it means that if somebody adopts, if a natural resource manager want to augment, and then he adopts model B, it means that he will not get enough individuals at the end of the day. It's better to go for model A. That is why it's very important to compare the order of event in which you can augment your population, so that you don't just stand up and then say, I want to do augmentation, let me do this. You may not get the best strategy. And then we can also see that the reserve population is better, because after augmentation, the still population level is very fine. Is the same happening to also to the predator population. After augmentation, it has increased. That's the population levels has increased. Now we also check another strategy. I'm coming. I think I need to move this one top. Oh, sorry, something is missing. I think my screen is missing because I was trying to shift and see the top. Shit. I wanted to show something up there and then the screen just got lost. Maybe I have to stop sharing and share again. Okay, sorry for that. Okay. Okay, so we want to consider also some of the effect of cost constants. So we are considering different scenarios on the model. So here we are considering effect of cost constants. So we can see that when we have model A, so here we increase the cost constant. At the beginning, we just increase from in model 50. We keep all the baseline parameters model 50 equation 15, and now we only set the linear cost term into 0 here. M2 is the linear cost term into 0 here. So you can see that, look at how the pre-population level has increased. When the linear cost term is set into 0, it has really increased very fine. And then the same type of predator population level is also increasing very well. And then the reserve population is also 0.4, which is very fine. And the reason is that enough individuals were able to be translocated when we use only the quadratic cost term, and that has increased the objective functional, that has made the difference be 31%. And then when you go to the model B, the same scenario, model B, what happened is that at the end of the day, we were having the population level 0.24, which is still even not up to the level in which the population can grow on their own. They are still below the threshold for growth. It means that in model B, it is not advisable to use that strategy, the order of event. It's better to still consider model A using the order of event. I have to wrap up. And then we also have this another scenario is that we also use the same baseline parameter. Then we check the augmentation factor, the constant for maximizing the reserve population. Initially, it was 0.10. Now we increase from, it was 0.50. Now we reduce from 0.50 to 0.10. So we can see that the way the pre-population level has increased, it has really increased very well. It has increased very well. That is almost 0.8. And then the predator population is also 0.65. So that is also the important played by the constant for maximizing the reserve population. And that has increased. Look at the percentage increase, 284%. It means that that will also make the cost very high because we are maximizing the reserve population. So the constant for maximizing the reserve population is very important. And when we also use the model B, still here, this is the only place we saw that the model B has been able to increase above the threshold for growth, just increase very well. But you can see that the cost is very high. If you want to adopt that one, the cost will also be very high. Usually, the predator population, we don't have problem with them because they are growing very well. The reserve population, they are growing very well, but the prey population is a problem. And then the controls, I'm not talking more about the controls because the controls show how the populations were translocated. And then we have another one is also, we also talk about the cure, the growth rate of the reserve population, and then the carrying capacity of the reserve population, because that is also very important. After reducing them from 0.85 to 0.70 and then 0.8 to 0.6, we just reduce them, and that is what also happened. We can see that after reducing the growth rate and the carrying capacity of the reserve population in model A, the population levels was less than the threshold for growth. So it means that it's not advisable to adopt this strategy. And similarly also happened to model B. It's not advisable. And then the last thing we also consider is here, we want to check the natural decay or the current rate of the predator. If the death rate is now reduced from 0.1 to 0.025, what will happen to both models? We want to see the death rate. You can see that the predator population is really affected. It's 0.4, though at the end of the augmentation, it's still above the threshold, so it can grow on their own. And then the prey population is also 0.35. It is very fine. But let's go to model B. The model B, when the death rate was reduced, this network has not been good. I think my network has not been good. Is it okay, Dr. Julius?
Yeah, but you're back. You're back. It's fine.
Sorry, there's no light here today, so I'm using mobile network. That is
Yeah,
why
it's okay. It's okay.
sorry for that.
Yeah,
Okay.
no problem.
All right. So it was rebound. You can see that after the death rate was also reduced from 0.025, so from 0.1 to 0.025, the predator population was reducing and then it was rebound again. And then that shows a very important scenario. So in conclusion, this study applies optimal control theory to a model of species augmentation for predator-prey model, where we consider two orders of events, where the first is to consider whether to augment and then predator-prey interaction happen, or before predator-prey interaction happen, or maybe growth will come first before augmentation, before predator-prey interaction. In fact, we have so many order of events. We have recommended them in one article I'll show. So there are so many order of events, but we consider these two order of events. They are very critical. And then the optimal control was aimed to maximize both the target and the reserve populations at the final time, whilst we are minimizing the associated cost. And then we use the simulation of the two models showed different population levels at the end of the augmentation. This means that the natural resource managers who are interested in maximizing the total population, they may opt for the strategy that gives a higher population levels. Of course, that was strategy A or the model A that gives a lot of individuals at the end of the augmentation strategy. And this work also lays foundations for optimal control theory applied to the model of space augmentation in interaction population model. In fact, this is the first of its kind about the when we talk about interaction populations with optimal control. And these are a few references. And then this work was also published in Taylor and Francis. So we published this work here. You can read it. And then if you also need a PDF, I can share with you. Thank you for your time.
Thank you very much, Dr. Munkaila, for your very interesting.
Hello.
Yes. I think
Is the floor open for questions?
I want to hear from Dr. Julius, but I think he's also when his network is not stable.
Okay, let me wait for him then.
Dr. Julius, can you hear us? Fista, can you also respond to? Maybe you can ask question whilst you are waiting for him.
Yeah, thank you, Dr. Dasumani.
Welcome.
I'm really impressed. I'm happy, and I congratulate you for this wonderful presentation. This is a very important aspect of mathematics. I can see you are trying to do a lot of things that has to do with optimization, optimal control, and a lot. The first observation I see here is, of course, you are looking at a discrete time. In this case, I think time is involved because it's possible to have an optimal control problem or optimization problem, probably constrained or unconstrained, but I can see you are dealing with constrained problem. And I want to ask, the first question I have here is the constraint, or are you dealing with ordinary constraint or unconstrained optimization problem? That is the first question. Maybe I can just run through those questions and you can answer them together.
Okay, maybe you can go ahead.
Yeah, and that is the first thing. Is it constrained problem or unconstrained problem? That is the first question. The second question that I can see you are talking about augmentation and augmentation of the problem. I'm looking at it that if you, instead of looking at augmentation, I mean augmented, which of course from the model model A and B, I can see the term, one of the term there, which is called augmented term. I'm looking at it. Is it possible to, rather than using augmentation or augmented, is it possible to use a penalty method? If you use penalty method in this kind of problem, will it also give us a very valid result? That is the second question, because I from my knowledge of the little knowledge I have about automation problem, I know we can as well use penalty method on augmented. As a matter of fact, my MSc work was on augmentation in augmented Lagrangian, so to say, because I'm interested in this work. But unfortunately, my case, in my own case, I was not looking at the time. I was looking at OD constraint because it was a constraint problem, and my constraint was ordinary differential equation. So, thirdly, will it be possible for us to look at PD constraint if at all you are dealing with constraint problem? So those are the three questions I want to ask from you. Presently, I'm thinking of taking the work further to look at PD constrained automation problem, which of course, I don't know, maybe you can shed more light on that. Maybe we can also look at things and because I know most of PD problems too. And I'm not also looking at online PD. I want to see how we can bring time into it. Probably we are looking at elliptic PD or instead of looking at Poisson or Poisson might just be, or you can look at heat equation as maybe our constraint might be a form of heat equation, which has to do with time. So if that is the case, how do we handle that? Thank you.
All right, thank you very much. Sorry, okay, I may switch to because we don't have a light here, power here. It's this constraint problem. That is why we're able to use the sequential quadratic programming because we need to. If you don't have constraints, it become very difficult. So I've defined all the boundary. When you look at the control, remember I gave you the maximum one. I gave you the constraint, and then all the populations are positives. I give the constraint from, when you look at that article, you see that I've defined all the constraint there. And then when we talk about the penalty method, whether it's the same as the penalty method, in fact, I think that would be a very good thing we need to also compare. We didn't compare with that, but I'm sure maybe not necessarily because if you consider it to be a penalty method, it may depends, but we didn't come from that angle, which maybe I've just noted it down. I'll just now be going to check to see if that can be the same as the penalty method. For the
Thank, thank,
PDE case, I think
yeah,
it's
continue.
yeah, for the PDE case, I think it's fine. Yes, we also thought of that. It's very possible and it's open. I've even added that one. I stated it clearly that especially explicit augmentation have not been studied here. So it's something that's in mind, and then I think it's because you can also add the space variables and the movement. That is very fine. That's where we were also thinking we can extend. It's possible to extend to that place.
Okay, let's take our final question from Dr. Ezekiel.
Thank you very much, Dr. Munkaila, for this great presentation. So, my question is about the model validation, or model validation, because after formulating model, you have maybe in a theoretical way to do some theoretical analysis, social stability, existence and uniqueness of the solution, all those stuff, in order to check the model. Yeah, or maybe if you don't have to validate the model theoretically, you can use a real data for a practical validation through some experiments. So in your case, I don't know if you did anything like that in order to check if your model is okay or not. So that
All
is
right. Thank you, Dr. Ezekiel. I think it's a very good question. Yes, I did that one. I did a stability analysis, positivity. I did those one to check. I did that one in the main work. In main cases, we did all those things, but here presented only the optimal control aspect.
okay. Thank you. This fine.
Okay, at this point, I'll just call on an expert in optimization. Professor Lekunle, I don't know if you are there. Maybe you want to just give maybe a word before we leave.
Yes, I am around. I just want to thank the presenter. This is one of the best presentation I've watched in this program. Don't blame me, maybe because it's my field. Thank you so much. Thank you so much for the presentation. As you yourself, you noted, there are still many areas one can go into to improve this work. And you have opened up so many areas we can see further dig into. I just want to say thank you. Thank you, Dr. Ehige. Thank every listener. God bless you all.
Thank you very much for your thoughtful words. And
Sorry,
I think yes,
sorry, Dr. Julius.
yes, please.
Sorry, for me, I don't know if it will be possible for us to have the email of this presenter. Personally, I want to follow up with him because
Okay, Dr.
his area
Munkaila,
is.
please, could you type your email on the chat box, please?
Okay, I'm doing that
Maybe
right
yes.
away.
Okay. All right. So next month we have a speaker from. In fact, this April we almost something just happened. This April we were supposed to have a speaker from the US, but he sent his topic very late, so I've now moved him to July. So next month we should be having Dr. Victor from France, I think. Yeah, to give us a talk. And maybe in June, we have Professor Yulong from the US. So I believe that in the next 3 months, we have a very interesting topic in numerical analysis. This time around numerical analysis. No, I think Dr. Victor will be talking on in machine learning, scientific learning, numerical analysis, and machine learning. while Professor Yulong and Dr. Luan will be talking, their topic will be based on numerical analysis. So I welcome you to be available next month for the next seminar series, and I will let you have the flyer as soon as everything is out. I want to thank you all for participating in this month's seminar series, and I wish you well in your research, and I pray that everything continues to go well with you in the mighty name of Jesus. Bye-bye.
Thank you. Thank you very much.
Thank you.
Thank
So,
you.
Dr.
Thank you.
Yes, Dr. Munkaila, I want to also say thank you very much for your very wonderful presentation, and I appreciate you in a short notice you actually delivered, and I thank you very much, and hope to see you very soon. Thank you.
Thank you. Thank you, Doctor. Thank you. I also thank you everyone for listening. Okay.
Bye-bye, everybody.
Okay. Bye. Bye.